Welcome to the tutorial video on Lesson 4.4, Irrational Numbers. In Lesson 4.4, you are going to be representing, identifying, and simplifying rational numbers, converting between powers with rational exponents and radicals, converting between mixed radicals and entire radicals, and solving problems involving radicals. This is part 1 of the tutorial videos, and part 2 will cover the examples in the second half of the Lesson 4.4 notes. There are many examples of irrational numbers in real life, and one of those is this painting called Coming Rain. You can read more about this painting on page 184 in the Mathematics 10 textbook, and it's talking about the golden ratio. So let's look at what an irrational number is. We already know what rational numbers are. They're just numbers that could be integers, whole numbers, natural numbers. You can have fractions or decimals that terminate or repeat the decimal numbers. So we know we've used rational numbers in the last section. In this section, we're looking at irrational numbers. And irrational numbers are all numbers that are not rational. In other words, they cannot be expressed as a fraction. So they cannot be written as in the fraction form, where a and b are integers, and of course the denominator b cannot equal 0. Irrational numbers, put another way, are non-terminating and non-repeating decimal numbers. Some examples of this, and probably the most common example of a non-repeating, non-terminating decimal, is pi. Pi is a decimal number that goes on forever and never repeats. It starts off with 3.1415 because it goes on and on and on. There's never any patterns that repeat in those decimal places. There are many other examples of irrational numbers. One is square root of 5. If you type in the square root of 5, you would get the decimal number 2.236, and it keeps going, and it will also be a number that never ends and never repeats in the decimal places. So root 5 cannot be written as a fraction. Included in your notes is a diagram that is from page 186 in the textbook, and it's just a visual of how the number sets are organized. We have our rational numbers here, is the purple rectangle, and rational numbers, again, integers, whole numbers, natural numbers, fractions, and decimals that end or repeat. And within the rational numbers, you have the integers. Within the integers, you have the whole numbers. And within the whole numbers, you have the natural numbers. Rational numbers are all of these. Irrational numbers are all the numbers that are not rational. So pi, square root of 2, square root of 5, square root of 2 over 3 is still irrational because even though we have a fraction in here, when you do take the square root of that fraction, it will no longer be able to be written as a fraction. All of the numbers from the rational numbers and all of the irrational numbers make up the real numbers. Real numbers are basically all numbers that we know of. We see a lot of irrational numbers when we're dealing with radicals. The rest of this section is dealing with what are radicals and how do we use them. A radical is a rational or an irrational number. Many of them are actually irrational, but not all of them. The square root of 4, which just equals 2, is still a rational number. But what is a radical? A radical is any number that has a root symbol, and with the root symbol comes an index, and under the root symbol is the radicand. So we're going to look at the parts of a radical here in a little diagram. First of all, we can have a root symbol, is this symbol right here. And then with that symbol can be an index or a number written just tucked into the front of the root sign. If you have a square root, the index is 2, and we don't write a number. But if we have an index anything bigger than 2, we do write the number there. Also, under the radical symbol is the radicand. So an example of a radicand might be 2x. So that part is the radicand. The whole thing, all put together, is what we call a radical. Remember, your index is an actual number. N is just representing the number. So just looking at our definitions, the radicand is the quantity under the root sign all the time, and that's what I wrote in red here. It can be just a number, it can be just a variable, or it could be a combination. But it will always be the quantity under the root sign. So in this last example, the square root of x, and then times by y, the y is not under the root sign, it's outside, so just the x is the radicand. And again, the index is what root you are taking. So if the index is 2, we commonly don't write it, and we just use the root sign to indicate a root of 2, or an index of 2. If you're taking the cubed root, your index is 3, the fourth root, your index is 4, etc. Fifth root, index is 5. And that just tells you how many factors that you have that are the same that can be multiplied to get the radicand. We just finished looking at what a radical is, and in the previous sections we've looked at our exponent laws. Now we're going to bring the two together because they are related. There's a rule that says that you can write powers with fractional exponents as radicals. And it can be kind of written in two ways. So you start with your power that has a fraction as an exponent, and you can break apart that exponent so that you have, say, x to the power of m, all raised to the power of 1 over n. This is the exponent law of power to a power. If you multiply those two exponents back together, you would get back to m over n. How can we write this now as a radical? Well, the denominator of our rational exponent will become the index of our root. So we're going to have the nth root of everything that was inside of the bracket, which becomes our radicand. So n to the nth root of x to the m is the equivalent radical to the power that we started with. Another way to write the radical from the rational exponent is when you start with x to the m over n, you can break it apart as x to the 1 over n, all raised to the power of m. This is still giving you the same form. Now we have the root with an index of n of the radicand, which is x, and the whole radical is raised to the power of m. These two forms are equivalent and originated from our power with a rational exponent. There's an acronym that you can use to help you remember which goes where, and that's DINE. It stands for denominator of the rational exponent, so the denominator of the fraction in the exponent becomes the index of the root. So here we had n in the denominator, n became our index. And the numerator in the fractional exponent became the exponent under the root sign or of the radicand. Okay, so let's practice converting from powers to radicals, and then we'll practice going the other way from radicals to powers. If we look at part A here, we have 2 to the power of 3 over 4. So we first look at our denominator of the exponent. It's a 4, so we're going to have the fourth root of whatever the base of the exponent was to the power of the numerator, so 2 to the power of 3. And that's your answer. We don't need to simplify, we're just converting forms. Part B, we have 64 to the power of 1/2. So the denominator here is 2. That means that our radical has an index of 2. So we just have the square root. We don't need to write the 2 in there. And then the base of the exponent becomes the radicand, and it's just to the power of 1, which 64 to the power of 1 just equals 64. So you can just write the square root of 64. Over here we have 8x squared in brackets, and then it's raised to the power of 1/3. So we look at the fraction exponent on the outside, and it has a 3 as a denominator, so we have a cubed root. And because the numerator is a 1, the whole cubed root would be raised to the power of 1, which isn't going to change the radical. Anything to the power of 1 is just itself. And the radicand is what was in the brackets, so 8x squared. So you can write that as the cubed root of 8x squared. The next one is similar, but this time our numerator is not a 1, it's a 3. So our denominator is 8, so we have the 8th root, and all of that root is going to be raised to the power of 3 because that was the numerator. The radicand is what's in the brackets, so x to the 4. Now we need to simplify this a little bit more. With this power outside here, we have to do something with it when it's not a 1. If you look back to the way you can convert it, it can be written in the form with the exponent on the outside, or you can bring that exponent into the exponent as the exponent of the radicand. So we can have the 8th root, and then the radicand was x to the power of 4, and the radicand gets cubed. Well, here we have a power to a power. So to simplify that, we get the 8th root of x to the power of 4 times 3, which is 12. And that would be our final answer for that one. For part E, we have a negative exponent. We don't want negative exponents, so using your exponent rules, we want to change that one to a positive before we change it to a radical. To change this to a positive exponent, we put it onto the opposite side of the fraction and make our exponent positive. Don't flip the fraction in the exponent, just put the whole thing on the bottom of a fraction. Then our radical is also going to be on the bottom of that fraction. We have the cubed root of x to the power of 4, which was the numerator. In the last example, we have a rational exponent of 1 over 5. So we're going to start with the 5th root, index was the denominator, of the radicand, which was x to the power of 4 over y to the power of 3. Now all of that would be raised to the power of 1, but because that doesn't change anything, we just have the 5th root of x to the 4 over y cubed. Going the opposite way, so converting from a radical to a power, you are still using the same rule, you're just going backwards the other way. So starting with a radical, you want to identify the index of the radical. In part A, this is just a square root, so our index is 2. Take the radicand, which is x, and it will be to the power of a fraction. So I'm going to start my fraction off there. The exponent of x is just 1, so that becomes the numerator, and the index, which is 2, becomes the denominator. So x to the power of 1/2 is the answer for A. Don't forget to use your acronym DINE. The index becomes the denominator, and vice versa, and the numerator is the exponent of the radicand. Let's look at example B. We have a square root, and our base of our exponent in the radicand is s. So the base of our exponent is going to be s. The exponent of the radicand was 3, so our numerator is 3, and the index of the root was 2. So we have s to the power of 3 over 2. Part C, we have the base of the radicand here is 3. So we're going to have 3 to the power of 4, which was the exponent, over 5, which is the index. For part D, we have a little bit more going on in the radicand. So we're going to take the base, which was 6x cubed, and that's going to be the base of our exponent. The reason we do this is because there's more than one thing in that radicand, so it's a product, we have to put it in brackets. And then, as if this whole radical was in brackets raised to the power of 1, our exponent of 6x cubed is 1 over 7. But we have to simplify that a little bit, so we have to multiply the 1 over 7 into all of the exponents in the brackets, because power to a power rule. So we get 6 to the power of 1 over 7, and x to the power of 3 times 1 over 7 is just 3 over 7. And that's your answer for part D. Finally, for part E, we have our base again is y, and it's going to be raised to the power of 5 is the numerator, and n is the index, so it becomes the denominator. That concludes part 1 of the lesson 4.4 tutorial. Please see part 2 for the rest of the examples from the notes package.